Definition of a hyperbola, Part 2. Here's where we derive the equations and the attributes of the hyperbola. So if you have this drawing where xy is a point on the hyperbola, and you have these distances to the foci, then the definition of the hyperbola is that the difference of the distance, absolute value, is a 2a. So that means that, for example, d1 minus d2 is going to be plus or minus 2a, and the plus and the minus gives you the two arms. So similar to the ellipse equation derivation, you just set up the distance formula. I'll just show you this one. This is d1. That's the distance over here from xy to focus f2 here, which is 0, negative 1. You can see it's x minus 0 and y minus a minus c. So similarly, there's the d2. You subtract and you get plus or minus 2a. During the derivation, the plus or minus aspect will cancel out as you square both sides, and it'll all turn out fine. Okay, so there's a similar derivation to the ellipse, and you should really try this and just follow the ellipse steps, but the only difference is that there's a minus sign here instead of a plus. If you can follow that through, that's going to be very good. When the quantity c squared minus a squared shows up, and it will, call it b squared, so that b squared is c squared minus a squared. And then b will have a special interpretation, because if you do that, the equation that finally results is this one right here. The a, which is the distance from the center to the vertice in the opening direction, the a lies under the positive term variable. Always, in any of the forms, a lies under the positive term variable. A could be less than b, or greater than b, or equal to b. It can be any of those, but a lies under the positive term, and the positive term is the y in this case. Okay, the foci are these points, and the defining relationship is that b squared, it was c squared minus a squared. And if you solve that for c squared, you get c squared is a squared plus b squared. So that'll, from the a and the b, that'll get you the foci. Okay, and so this is called standard form of the equation, and it's for the one that's opening in the y direction. As we can see, it's opening up in the y direction. Okay, now, similarly, if the hyperbola opens in the x horizontal direction, you follow the same kind of derivation, and it all comes out this way. A lies under the positive term variable, but this time the x is the positive term variable. The foci are now at c0 and negative c0. The a vertices are in the opening direction right here, and c squared is still a squared plus b squared. B squared is c squared minus a squared in the derivation. So this is a standard form of the hyperbola opening in the x horizontal direction. A lies under the positive term variable. Can b be illustrated on the graph, and what's the interpretation of the b? Yes, it can. Okay, draw a circle of radius c. C is the distance out to the foci, with the center at the center of the hyperbola as shown. So draw this circle around here. Number 2, draw a rectangle with width 2a inscribed in the circle. So you take this 2a here from vertice to vertice, and you extend out a rectangle until it touches to the circle. Draw a segment from the center of the circle to a corner of the rectangle as shown. That's from here to there. Okay, so now we have a right triangle. That's the right triangle right in there. And we solve for the unknown side, the little X there. So we have A here, C here. Now why is this C? Because C is a radius of this circle, and we're going out to the circle, so C is a radius there also. So you have A, unknown X, and C is the hypotenuse of the right triangle. So A squared plus X squared is C squared. X squared equals C squared minus A squared. But we recognize that from earlier. C squared minus A squared is the B squared in the derivation of the equations. So X is B. So that's B over there. So we can just write that as B. That side right there is B. Okay. So the length of the rectangle is 2B all the way across here from, say, here to here. That's 2B. Okay. Now, that's also useful for another reason. The hyperbola approaches asymptote lines, which we use to draw the hyperbola. Okay, how does that work? Let's take this opening upward and downward hyperbola, and we're going to add the x squared over b squared over to the other side. So now we have this. Now, as x goes to infinity, way out here and way out here, this is going to be x equals going to be like 1,000,000, 2,000,000, a googolplex. It's going to be so large that this 1, it's called a limiting process. This 1 will shrink to insignificance. So the y squared over a squared is essentially approximately equal to x squared over b squared without the 1, since the numbers are so large. So if we just multiply both sides by a squared, we're going to get this in the approximation. Take the square root of both sides, and you're going to get y is plus or minus a over b x. And you can see there's an a and a b here, so something's going on with the slope there, a over b. So anyway, y equals plus or minus a over b x are the asymptote lines that the hyperbola arms approach as x goes to plus or minus infinity. For the opening in the x direction case, we have this standard form. We solve for the y squared over b squared, you get this. And again, the negative 1 will shrink to insignificance, and this time the b squared multiplies over, and the b is on the top. The b is on the top, as it would be for the opening in the x direction case, because the a vertices will be in the x direction, so b will be going in the y direction, so b is the numerator. Okay, so how we draw the hyperbola. We draw the vertice points, because we're going to know a in the equation, because a lies under the positive term variable. So we're going to know this a, so we're going to mark those off. A always lies under the positive term variable when the hyperbola equation is in standard form. Then draw the rectangle with width 2a. So that's this rectangle. So you make it touch out to the vertices and make it be 2b long. So you're going to count over b, and that's how you know when to end the rectangle. It's 2b long and 2a wide. Draw the asymptotes through the corners of the rectangle. It's through here and through the center and through there and here, through the center and down there. Then draw the hyperbola arms outward asymptotically to the asymptote lines. So you're going to have this picture here with the crossing asymptotes, and you're going to have your vertice, and you're just going to trace out there, put a little arrow on there, go out here approaching the line, put an arrow on it, go out here approaching the line, and go out here approaching the line and put an arrow on it. That's how you're going to draw the hyperbola. So the next video shows, for a specific example, how we do it.